Hello, everyone. Welcome back to part 3 of solving logarithmic equations. In this little tidbit here, we're going to talk about, you guessed it, multiple logs or natural logs on one side. What are we going to do if we're solving a logarithmic equation? We have a bunch of logs on any given side. What's the deal? So sometimes there will be multiple logarithms in an equation. It could be on the left side, it could be on the right. Heck, it could be on both. In this case, if there are multiple logarithms in an equation, you're going to need to apply the logarithm properties in order to rewrite the equation with a single logarithm. And then you're going to have two possible situations. If there's a log on the left, a bunch of logs on the left and a single log on the right, you will end up with condensing the left to be a log equal to a log, where you're going to create a new equation like in part 2. Or if you have a bunch of logs on one side and a number on the right-hand side, then you can once you condense the left side, or vice versa, you can rewrite the equation with a single logarithm and convert to exponential form. So there are times in which we have multiple logs, and this is how we're going to combat them. Okay, we have to apply logarithm properties to condense them, and then either convert to exponential or create a new equation, depending on what we've got. So let's jump into it, shall we? Our first example is going to be log base 7 of x plus log base 7 of 3 is equal to log base 7 of 24. Okay, now it's not necessary. This is how it might show up. I like to put parentheses around my inputs. I just do. It's just a habit. Old habits die hard. I don't even remember where I learned it from, but I like them. Okay, so feel free, if that floats your fancy as well, do it. Now, we're going to need a reminder on what the logarithm properties are, because you'll notice on the left, I have a log plus a log equals a log. Okay, so I have multiple logs on the left side of my equation, which means on the left side, I'm going to have to apply the logarithm properties to condense it. So, luckily for you, I have the properties of logs on a little sticky note, and I suggest if you don't have them, you do that too. It makes it really nice and easy. So I can see that I have a log plus a log. So looking at my properties of logs, the very first one, the product property, has a log plus a log. Cool. So I'll use the product property to condense the equation to log base b of like the first log times the second log. So let's do that. Let's use the product property to condense the left-hand side into a single logarithm before doing whatever we got to do. So by the product property, notice I write the word log one time. Condensing means I write the log one time. So log including its base 7. And we're going to multiply them together. Whatever comes first gets multiplied first, which is x. Whatever comes second gets multiplied second, which is 3. And then I have equal to log base 7 of 24, and that's by the product property of logs. Okay? Cool. And then I really like x times 3. Usually we write the number first, so I'm just going to rewrite it as log base 7 of 3x is equal to log base 7 of 24. That's me just rewriting. Same thing. Multiplication can be flip-flopped around. 1 times 2 is the same as 2 times 1. Okay? Now, remember, apply the logarithm properties in order to rewrite the equation with a single logarithm, right? Single log equals single log. Cool. Now we're back to the problems we just came from, which says if I have a single log equal to a single log, I can create a new equation of the inputs and just solve that. So I'm going to take my inputs. On the left, it's 3x, and the inputs on the right, 24, and set them equal to each other because they both are log with base 7. And alas, to figure out exactly what my variable is equal to, I'm going to divide by 3. I get x equals whatever 24 divided by 3 is, and looks like that's 8. Just a single 8. That is awesome. Now remember, okay, I'm going to keep bringing it up because it's important, all right? So there is a possibility that there may be an extraneous solution. It probably won't happen here, but remember, extraneous solutions arise most often when we apply properties of logarithms or have a quadratic equation to solve. Look, product property of logs. We used a property of logarithms, so I need to check my answer. Although my answer is a positive value, doesn't necessarily mean it's not going to lead to a positive input. So I should just always get in the habit of checking if I use properties of logs, or if I have a quadratic, I better just check it. And remember, you have to check it in the original. So I'm checking if log base 7 of 8 from the x plus log base 7 of 3 is equal to log base 7 of 24. Now, I can use my product property of logs to become log base 7 of 8 times 3. And I'm hoping this is log base 7 of 24. And luckily for us, 8 times 3 is 24. So we can see log base 7 of 24 is really equal to log base 7 of 24. So my answer is not extraneous. I kind of thought that it might not be extraneous because it's a positive value, but I gotta check. Gotta just get in the habit of checking. Cool. Let's do another example, shall we? Another example. Let's do a log of x minus 3 plus log of x is equal to 1. Okay, notice on the left I have multiple logarithms in an equation. I'm going to have to apply log properties to write it as a single log. Again, looking at my properties, I have a log plus a log. Addition is the same as multiplication, or I can convert an addition problem to multiplication. So I'll use my product property again. I'm going to say that log with the base of 10 of x minus 3 times x is equal to 1. You can even write in the little base 10 if you want. And just for good old time's sake, I'm going to say that this is by the product property of logs. And I'm just going to rewrite this as log base 10 of x times x is x squared, negative 3 times x is negative 3x. And I'm going to write it in a set of parentheses so I don't forget to distribute. Now, once you have the equation with a single log, I can either convert to exponential or create a new equation. In this instance, since I have a log equal to a value, I'm going to convert. So 10 to the first power should be equal to x squared minus 3x when I roll my log, or if I exponentiated both sides, 10 would become the base and we would get the same thing. Now remember, whenever you have a quadratic, ladies and gents, you're going to have to factor, okay? So let's just move this bad boy over. So I'm going to write this as by converting to exponential. And this is just, this step right here was by simplifying. Okay, so I'm going to need to factor. So I'm going to subtract 10 from both sides. I end up with 0 is equal to x squared minus 3x minus 10, and I need to factor this. What are things that multiply to 10 that add up to 3? Well, 5 times 2 is 10, but I need it to be a negative number. So negative 5 times positive 2 is negative 10, and negative 5 plus positive 2 is negative 3. So I have 0 is equal to x minus 5 and x plus 2. By the zero product property, I will set each factor equal to 0. That's the only way that would hold true. And doing so, I get x equals positive 5 and x equals negative 2 as my possible solutions. Again, extraneous solutions. They can arise when we apply properties of logarithms, which we did, and have a quadratic equation to solve, which we did. So I need to check that both of my equations are not extraneous. Remember that negative numbers or inputs are undefined. They're only defined for positive inputs, positive numbers. So I have to make sure that both of my numbers here don't give me a negative input, because otherwise I'm going to have an undefined log. So I'm going to check in log of x minus 3 plus log of x is equal to 1. I'm going to check in that equation, and I'm going to plug in 5 first. So 5 minus 2, log of 5 minus 2 plus log of 5, is that equal to 1? 5 minus 2 is 3, so I have log of 3 plus log of 5. Is that equal to 1? And I could use the properties of logs again and do log of 15, because 3 times 5 is 15. Is that equal to 1? And check. I could check with my calculator, okay? You might not know that this is true. You just find the log button, type in your input, and I get 1.7609. Uh-oh, that's not good. What about here? Let's try this. Log of 3 plus log of 5. Uh-oh, 1.76091259. That's not true, right? That is not true. I still got 1.17. That's not equal to 1, so that's a false statement. That guy doesn't work. That does not work for me. Oh, first of all, I should probably write down the right number here. So let me redo this. If it was, oof, mistakes are part of learning. Are we right? Oops. Let me fix this. Okay, hold up. I was going to say, that's kind of weird. I would suspect that the negative value might be an extraneous solution, but it can happen sometimes. But let me do 5 minus 3, not 5 minus 2. So 5 minus 3 is 2. So I really need to check if log of 10 is equal to 1. And let me see. Log of 10. Yep, that's true. You could also remember that a log without a base is 10. So 10 to the first power should equal 10. Or like I did earlier, you could also literally type in log of 2 plus log not natural log of 5. And you'll see that also log of 2 plus log of 5 gives me 1. So this is a true solution. However, I want to check that negative 2 works as well. So negative 2 minus 3 is going to be log of negative 5. And log of negative 2 is what I'm plugging in on the right. Now, remember, logs are only defined for positive numbers or positive inputs. Negative numbers or negative inputs are undefined. So this isn't going to work for me. And if you don't believe me, use your calculator. Log of negative 5, right? This first one that I have right here, log of negative 5, error, undefined. Log of negative 2, right? If I plugged in negative 2, error, undefined. So negative 2 is our extraneous solution in this situation. it's usually the negative numbers, but not always, because we saw in one example previously that a negative number worked out. It did. So we just gotta be careful and make sure that we're checking them always. Let's do 1, 2, 3, 4 more examples. They're gonna get a little bit more challenging.